On June 6, 1944, over 156,000 Allied troops landed on the beaches of Normandy in the largest amphibious invasion in history. Coordinating this massive operation, involving thousands of ships, aircraft, and vehicles crossing the English Channel in darkness and landing at precisely the right locations, required technologies that most soldiers never knew existed. Behind the visible drama of the beach landings was an invisible network of navigation systems, communications equipment, deception technologies, and coordination tools that made the invasion possible. Today we're uncovering the secret technologies that coordinated Allied invasions throughout the European and Pacific theaters. Innovations in navigation, communications, intelligence, and logistics that transformed amphibious warfare and made operations of unprecedented scale and complexity achievable. The GE navigation system was a British invention that revolutionized precision navigation. The system used 3 ground stations transmitting synchronized radio pulses. Aircraft or ships equipped with GEE receivers measured the tiny time differences between these pulses and used special charts to determine their position. With accuracy of a few hundred yards, extraordinary precision for the era. GE became operational in 1942 and was immediately valuable for bomber navigation over Europe. The GE chart showed curved lines representing points of equal time difference between transmitter signals. By identifying which lines intersected at the receiver's position, navigators could determine their exact location. This mathematical elegance, using the geometry of signal timing to create a position fix, was conceptually brilliant and practically effective. Navigators trained to read these unusual charts could maintain accurate position even when flying through clouds or over featureless ocean. For invasion operations, GE provided critical capability. Bomber streams could be routed precisely to avoid friendly ships and aircraft. Pathfinder aircraft could mark landing zones accurately, even in darkness or poor weather. Transport aircraft dropping paratroopers could release them over the correct drop zones despite enemy resistance and navigation difficulties. The system's range, up to 400 miles from transmitters, covered much of the invasion areas in both Normandy and later operations. GE transformed navigation from estimated art to measured science. The SCR-584 was an American automatic tracking radar that provided precision air defense for invasion forces. This mobile system could be towed to forward locations and set up quickly, providing immediate protection against enemy aircraft. The radar could automatically track a single target, with extraordinary precision, directing anti-shooter aircraft guns to hit aircraft that human gunners couldn't even see. For invasion operations, protecting the beachhead and supporting naval forces from air attack was critical. When linked to automatic gun directors, the SCR-584 created a deadly air defense system. The radar would lock onto an enemy aircraft, track it automatically while calculating its future position, and direct guns to fire at that predicted point. This blind firing capability meant that anti-aircraft batteries could engage targets in darkness, clouds, or smoke, conditions that previously made the air defense ineffective. During the Normandy invasion and subsequent operations, SCR-584-equipped batteries provided umbrella protection over Allied forces. The system required trained operators who monitored displays and adjusted settings, but once locked onto a target, tracking was automatic. This removed human reaction time from the equation and ensured consistent accuracy. The SCR-584's mobility meant it could advance with ground forces, providing continuous air defense as the front moved forward. Multiple systems could be networked to provide overlapping coverage, creating defense zones that enemy aircraft penetrated at their peril. This radar system represented the cutting edge of air defense technology and was a closely guarded secret. The variable time VT, or proximity fuse, was perhaps the most revolutionary technology of the invasion period. This miniature radar system, small enough to fit in an artillery shell, detected when it was near a target and detonated automatically. Before proximity fuses, anti-aircraft shells used time fuses that had to be set to explode at a predicted altitude, a hit-or-miss proposition. The proximity fuse turned near misses into kills by detonating when passing within lethal range of an aircraft. Manufacturing these devices was an extraordinary achievement. Each fuse contained 32 precision parts, including miniature vacuum tubes, all assembled to withstand the shock of being fired from a gun, forces exceeding 20,000 G. The fuse had to survive this violent acceleration, activate properly in flight, detect the target accurately, and detonate at the optimal moment. Mass production of such sophisticated devices required innovations in manufacturing and quality control that pushed industrial capabilities to their limits. The impact on air defense was dramatic. Anti-aircraft effectiveness increased by a factor of 5. Shells that previously had to directly hit an aircraft to destroy it now needed only to pass nearby. For invasion forces vulnerable to air attack, this technology provided critical protection. The VT fuse was so valuable that it was initially restricted to naval use over water, where unexploded shells couldn't be recovered and reverse-engineered by the enemy. Only during the Normandy invasion was it cleared for land use, immediately proving its worth against German V-1 flying bombs. Joint assault signal companies were specialized units that coordinated naval gunfire support for ground forces during amphibious operations. These teams landed with the initial assault waves, carrying sophisticated radio equipment that allowed them to communicate directly with offshore naval vessels. They could call for fire support, adjust naval gunfire onto targets, and direct the massive firepower of battleships and cruisers to support infantry advancing inland. The technology enabling this coordination included powerful radio transmitters, reliable crystals for frequency control, and standardized communications procedures. JASCO teams used multiple radio frequencies, one for communicating with ships, another for coordinating with ground forces, and sometimes additional frequencies for air support. This multi-frequency capability required sophisticated radio equipment that was both powerful enough to reach ships offshore and compact enough to be man-portable. The effectiveness of JASCO teams was proven repeatedly in both European and Pacific invasions. German fortifications that held up infantry advances were destroyed by naval gunfire, precisely directed from shore. Japanese bunkers that seemed impervious to small arms fire were demolished by 14-inch shells called in by JASCO spotters. This capability to bring naval firepower inland, guided by observers who could see targets and adjust fire in real time, gave amphibious forces a tremendous advantage. The technology that made it possible reliable battlefield radios was as critical as the big guns themselves. The mulberry harbours were massive artificial port facilities built in England, towed across the English Channel, and sunk in place off the Normandy beaches. These structures allowed cargo ships to unload directly to piers rather than relying on landing craft, a dramatic increase in logistics capacity. The technology involved was staggering. Massive concrete caissons, called Phoenix units, each weighing thousands of tons, had to be floated across the channel and precisely positioned. The Phoenix caissons were hollow concrete structures that floated when empty but could be sunk by flooding internal compartments. Once positioned in a line, they formed a breakwater protecting an artificial harbour. Floating roadways called whales connected the breakwater to the shore, allowing vehicles to drive directly from ships to the beach. The entire system was designed to withstand the notorious channel weather and provide harbour capacity equivalent to a major port. The engineering technologies that made Mulberry harbours possible included sophisticated concrete formulation for the caissons, innovative flotation control systems, and flexible pier designs that could accommodate tidal changes of up to 20 feet. Positioning the massive caissons required precise navigation and coordinated sinking. Too fast and they'd crack, too slow and they'd drift off position. The successful deployment of these harbours within days of the invasion was an engineering triumph that dramatically improved logistics. By the end of June 1944, the Mulberry harbours were handling more cargo than any port in England. The WWII, nicknamed the Duck, was an amphibious truck that could drive into the water, swim to shore and drive inland without stopping. This six-wheel drive vehicle, based on a standard GMC truck chassis, incorporated technologies that made true amphibious capability practical: a boat-shaped hull, propeller drive, and pumping systems to prevent swamping. The WWII could carry 2.5 tons of cargo or 25 troops from ship to shore and beyond. The technological innovation wasn't just the hull shape, it was the tire pressure control system that allowed the driver to adjust tire inflation while moving. Low pressure improved traction on sand. Higher pressure was better for road travel. The power takeoff system that engaged the propeller was another critical innovation, allowing seamless transition between land and water modes. These technical details made the WWII far more than a truck with a boat hull. It was a sophisticated, amphibious vehicle that revolutionized beach logistics. The LVT, landing vehicle tracked, was even more capable, using tracks instead of wheels for better cross-country mobility. These vehicles could drive across coral reefs, through surf, and over beach obstacles that stopped wheeled vehicles. Later versions, like the LVT-A, minus four-mounted weapons providing direct fire support for troops storming beaches. The LVT's ability to swim to shore and immediately advance inland without pausing to unload made it invaluable in Pacific Island invasions, where beaches were often hostile and narrow. Naval fire control computers were electromechanical marvels that calculated firing solutions for ships' guns. These devices took inputs including range, bearing, target speed and course, ship's motion, wind, and even the Earth's rotation, then calculated the precise gun elevation and timing needed to hit the target. The Mark I, a computer used in American battleships, was a mechanical analog computer with hundreds of gears, cams, and differentials performing continuous calculations. For invasion support, these computers allowed battleships to engage targets far inland with remarkable accuracy. Forward observers ashore would radio target coordinates, and the fire control computer would calculate the firing solution, accounting for the ship's position, motion, and even the different powder temperatures in different magazines. This technology transformed naval gunfire from an imprecise bombardment weapon into a precision fire support tool. The computer's continuous calculation capability meant that ships could fire accurately while both they and their targets were moving. This was essential for supporting rapidly advancing ground forces. The computer constantly updated firing solutions as the tactical situation changed. The mechanical sophistication required to perform these calculations in real time using 1940s technology is extraordinary. These fire control computers were classified technology, providing Allied forces with accuracy advantages that German and Japanese naval forces couldn't match. Identification friend or foe, IFF, was a radar-based system that allowed friendly aircraft and ships to identify each other automatically. When interrogated by radar, an IFF transponder would send back a coded signal identifying the aircraft or ship as friendly. This prevented friendly fire incidents and allowed defenders to distinguish genuine threats from friendly forces, critical during massive operations. With thousands of aircraft and ships operating in close proximity, the technology used radar interrogation frequencies and coded pulse responses. An incoming aircraft would be detected by radar, the radar operator would trigger an IFF interrogation, and friendly aircraft would respond with the proper code. Aircraft without IFF or with incorrect codes would be treated as hostile. The system wasn't perfect, codes could be compromised, and transponders could malfunction, but it dramatically reduced confusion in crowded airspace. For D-Day and other major operations, IFF was essential. With thousands of Allied aircraft over the invasion area, distinguishing friend from foe by visual identification alone would have been impossible, especially at night or in poor weather. IFF allowed fighter controllers to identify and track friendly aircraft, vector them to threats, and avoid shooting down friendly planes. The system also helped prevent naval forces from firing on their own aircraft, a real danger given the nervous state of anti-aircraft crews during invasion operations. The Rebecca Eureka system was a radar-based navigation aid used primarily for paratrooper and glider operations. Pathfinder teams parachuting ahead of main forces would set up Eureka transponder beacons on drop zones. Following aircraft equipped with Rebecca receivers could home directly to these beacons, ensuring accurate drops even in darkness or clouds. This technology was critical for the success of airborne operations during invasions. The Rebecca receiver displayed bearing and range to Eureka beacons, allowing pilots to navigate directly to drop zones without relying on visual landmarks or dead reckoning. This was revolutionary for night operations where visual navigation was impossible. The system operated at radar frequencies, making it difficult to jam or deceive, and had sufficient range to guide aircraft from their initial approach to the drop zone. During the Normandy invasion, Rebecca Eureka guided paratrooper drops despite heavy cloud cover and German anti-aircraft fire. While drops were still scattered due to evasive maneuvering and other factors, the system ensured that aircraft found the correct general area. Without Rebecca Eureka, night drops would have been even more scattered and chaotic. The technology gave Pathfinder teams the confidence that following aircraft would find them and gave transport pilots the navigation aid they needed in extremely challenging conditions. Reliable tactical radio communications were essential for coordinating complex invasion operations. The SCR-300 walkie-talkie provided infantry units with portable voice communications over ranges of several miles. This allowed company and battalion commanders to coordinate movements, call for support, and adapt to changing situations in real time. Before reliable tactical radios, battlefield communications relied on runners, signal flags, or telephone wire, all slow and vulnerable. Armored vehicles equipped with radios could coordinate their movements, respond to threats collectively, and receive orders while on the move. This transformed armored warfare from individual tank actions into coordinated unit maneuvers. During invasion operations, tanks equipped with radios could be directed to critical points, called to support infantry encountering resistance, or warned of enemy counterattacks. The tactical flexibility provided by radio communications multiplied the effectiveness of armored forces. Ship-to-shore communications linked landing forces with naval support and higher headquarters. Complex operations involving multiple beaches, diverse units, and constantly changing situations required communications networks that could carry high volumes of messages reliably and quickly. The technology included not just the radio equipment, but also communications protocols. code systems for security, and trained signalmen who maintained communications even under fire. The invasion communications network was an invisible but essential part of the operation. Pipeline under the ocean, Pluto, was an engineering marvel that pumped fuel directly from England to France, eliminating the need to transport millions of gallons in tankers and drums. This massive infrastructure project involved laying pipelines across the English Channel seabed, a technical challenge that required innovations in pipe manufacturing, laying techniques, and pumping technology. Multiple pipelines were eventually laid, delivering 8,000 tons of fuel daily to support Allied armies in France. The pipeline used flexible steel pipe wound on massive drums, mounted on floating platforms, codenamed conundrums. These platforms were towed across the channel while unwinding pipe onto the seabed behind them. The pipe had to withstand saltwater corrosion, resist damage from anchors and fishing gear, and maintain integrity despite tidal currents and shifting seabeds. Special pumping stations on both sides of the channel maintained pressure to push fuel through pipes that were over 100 miles long in some cases. Pluto's strategic impact was immense. Fuel was the lifeblood of mechanized warfare, and the armies advancing across France consumed staggering quantities. Conventional tanker delivery was slow, vulnerable to weather and attack, and consumed shipping capacity needed for other supplies. The undersea pipelines delivered fuel continuously, reliably, and efficiently, enabling the rapid Allied advance across France and into Germany. This infrastructure technology, though less dramatic than weapon systems, was equally critical to invasion success. The sigaba cipher machine provided secure high-level communications for Allied forces. This electromechanical encryption device produced coded messages that German and Japanese cryptanalysts never broke, ensuring that invasion plans, troop movements, and strategic decisions remained secret. Sigaba was technologically more sophisticated than the German Enigma machine, using multiple rotor banks and complex stepping mechanisms that created encryption patterns too complex for enemy codebreakers to solve. For invasion planning and execution, secure communications were essential. Commanders needed to coordinate across vast distances, sharing sensitive information about troop locations, attack timings, and strategic intentions. Sigaba allowed this communication to occur over radio channels that enemies could intercept but not decrypt. The confidence that high-level communications were secure enabled more aggressive and complex operational planning. The technology involved precise mechanical engineering, electrical switching, and cryptographic theory. Sigaba machines were large, heavy, and required trained operators, but they were deployed wherever secure communications were essential, from supreme headquarters down to corps and division command posts. The invasion of Normandy and subsequent operations depended on this communication security. Had the Germans been able to decrypt Allied messages, as the Allies could decrypt German Enigma traffic, invasion operations would have been far more dangerous and potentially unsuccessful. Specialized reconnaissance, aircraft equipped with advanced cameras provided detailed intelligence about enemy defenses, beach conditions, and potential invasion sites. These aircraft flew at extreme altitudes with powerful cameras capturing overlapping photographs that could be assembled into detailed maps and 3D views using stereoscopic analysis. The cameras used were technological marvels. Some could photograph areas miles wide with sufficient resolution to identify individual defensive positions. Photo interpretation specialists analyzed thousands of photographs, identifying fortifications, troop concentrations, supply dumps, and other intelligence. Before the Normandy invasion, virtually every yard of the French coast was photographed multiple times, allowing planners to understand exactly what defences existed and where. This photo reconnaissance detected the extensive obstacles planted on beaches and revealed the locations of coastal batteries that would threaten landing forces. The technology involved not just the cameras and aircraft, but also the photo interpretation techniques and equipment. Stereoscopes allowed analysts to view pairs of overlapping photos in 3D, revealing details invisible in single images. Specialized measuring tools allowed precise determination of heights, distances, and dimensions from aerial photographs. This intelligence gathering and analysis technology provided commanders with unprecedented knowledge of enemy positions and capabilities, allowing detailed invasion planning that would have been impossible relying on maps and agent reports alone. Operation Fortitude used technological deception to convince Germans that the main invasion would occur at Pas-de-Calais rather than Normandy. This involved fake radio traffic simulating entire armies, inflatable rubber tanks and landing craft, creating fake formations visible to aerial reconnaissance, and even special effects generating false radio signals. The technology of deception was as important as the technology of invasion. Keeping German forces away from Normandy increased invasion chances of success dramatically. The fake radio traffic was particularly sophisticated. Skilled operators generated message traffic patterns matching those of real headquarters and units, creating the radio signature of massive forces preparing for invasion in southeast England. Germans monitoring Allied radio frequencies detected exactly what they expected: a major force assembling opposite Pas-de-Calais. Combined with dummy equipment visible from the air and false intelligence fed through double agents, the deception was extraordinarily convincing. The success of Operation Fortitude meant that German reinforcements were held away from Normandy even after the invasion began. Hitler believed the Normandy landings were a feint and the main invasion would still come at Pas-de-Calais. This deception, achieved through coordinated use of multiple technologies, gave Allied forces time to establish their beachhead and build up strength before facing full German resistance. Deception technology proved that invasion success depended as much on confusing the enemy as on defeating them in direct combat. The technologies that coordinated Allied invasions represented a revolution in military operations. Navigation systems like GE and Rebecca Eureka allowed precise positioning in darkness and poor weather. Communications equipment from tactical radios to secure cipher machines enabled coordination across vast distances and organizational levels. Fire control computers and radar systems provided accuracy and detection capabilities that previous generations couldn't imagine. Logistics technologies like Pluto pipelines and Mulberry harbors sustained forces ashore. Deception technologies confused and misdirected enemy responses. What made these technologies so effective wasn't just their individual capabilities. It was how they worked together as an integrated system. Navigation guided forces to landing zones, communications coordinated their actions. Fire support protected them during vulnerable moments. Logistics sustained them after landing. And intelligence plus deception shaped the enemy's response. This systems-level integration was itself a technological achievement, requiring standardization, interoperability, and careful planning. The human element remained critical. Technologies were tools used by trained personnel who understood both capabilities and limitations. Radio operators maintained communications under fire. Radar technicians kept systems operational despite damage and harsh conditions. Photo interpreters extracted crucial intelligence from thousands of images. Engineers positioned massive harbour components with precision. The technologies empowered human capability, but didn't replace human judgment and courage. The legacy of these invasion coordination technologies extends far beyond the 1940s. Modern amphibious operations use descendants of these systems: GPS navigation replacing GE, satellite communications replacing radio, computer fire control replacing mechanical computers. But the fundamental principle remains the same. Complex operations involving thousands of personnel, numerous platforms, and multiple services require technologies that enable coordination, provide information, and ensure that everyone is working toward the same objectives at the right time and place. The secret technologies that made Allied invasions possible established the foundation for modern joint operations and continue to influence how militaries coordinate complex operations today.